Okay, welcome. Today is Thursday, the 7th of May. We have one last unit to complete before the end of this term. Um, just kind of giving you a heads up. Officially, Q7 ends tomorrow, 5/8. Um, and then Q8, quarter 8, is from May 11th through May 20th. Um, the all of the grades are going to be entered into the Q7 grade, and the idea behind it is that your grades will the grades that we do from this point on will replace um, a grade that's lower. So if you do better on this part, things like that. Say you take the second summative and you do better on this summative, it's going to replace that one. Now, I do want to clarify for dual enrollment, you still have two tests left to take. You have the cumulative exam that covers units 9 through 12, and you have the Chem 101 final. This is only for dual enrollment. Now, both of these are going to have to be completed by May 20th. All right. So I'm gonna have that. What I'm planning on doing is I'm planning on this material being done, being able to finish this material by Tuesday of next week, um, giving you some time to practice and review for the test. That would be for test 3, which is units 9 through 12, um, and then and for the non-DE students, it would just be a test on units 11 and 12, gas laws and intermolecular forces. But for the DE students, it's going to be 9 through 12. So the test that we previously took plus some other questions, and then the final will be on the final for DE only. Um, Final for DE only will be on May 20th, or it has to be done by May 20th. I'm going to open it up sooner than that. For DE students, what I would recommend is going back and looking at your previous tests in Moodle, and you can see the questions. You should be able to see the answers. I'll verify that with the student side account just to make sure what you can see. But I'm pretty sure you can see the test that you've previously taken in this course and see the answers, and it does give you some feedback, especially on the ones that you got wrong. Go back and look at all the quizzes under each of the testing tabs in Moodle and do those, and that'll prepare you for that final. Most of you, to be able to make an A or B in the dual enrollment class and the Chem 101 class from Southeastern, most of you won't have to do, but you won't have to score out of the box on the final to still maintain an A. Because remember, your homework scores count as one test grade, and then your best 2 exams out of the other 3 count as 2 of them, and your final counts as a quarter of the grade. So if you've done well on all the tests so far, the final is nothing to sweat. All right, so getting into this material for everybody. This is going to be Unit 11 for us. And I know I did it kind of backwards, that I did Unit 12 first, but this is actually Unit 11, and it's dealing with gas laws. So here are our outcomes that I'm kind of expecting to get through with this video today. Use Boyle's law to calculate volume and pressure changes at constant temperature. Use Charles's law to calculate volume and temperature changes at constant pressure. Use Gay-Lussec's law to calculate pressure temperature changes at constant volume. And then the combined gas law that kind of incorporates all of them, that you can calculate volume, temperature, and pressure changes from a initial setting to a new setting. All right. Now, typically in our class, we would have had it set up where I had you do your opening question and all that. I'm not going to do that, but I'll put this one up there just for you to kind of think about. How will changing the energy of the molecules in a gas be measured? What do we do to measure the change, or how do we measure the change in energy of a gas? So what is the relationship of those molecules to an energy change? Take a minute, pause the video, think about it, and then we'll come back to it. All right. So how will change in the energy of the molecules in a gas be measured? Well, we would see it in a couple of different ways. When we change the energy in the molecules, we're going to see increased molecule motion. One of those things is that if it's just increased molecule motion is going to increase the temperature. Because remember, temperature is a measure of the average kinetic energy of a substance. All right. So as kinetic energy of a substance increases, so does temperature. Depending on what type of container that we're in, if we're in a container that's of a fixed size versus one that's expandable, another way that increasing the energy would affect it is it's going to change the pressure. So what I kind of wanted to do with this question, and hopefully you kind of tried it at least or thought about it, is what I wanted to do with this is introduce that there are three main variables that we're going to deal with this, with gases, and that's pressure, temperature, and volume. All right. So all three of those are going to be impacted. Like if we manipulate the volume, we can manipulate the temperature and pressure. If we change the temperature or pressure and or both. If we change the pressure, we also change the temperature or volume. If we change the temperature, we affect the pressure. We affect the pressure and the volume as well, depending on, again, volume, and depends on the type of container, whether it's a fixed volume like a canister, like a propane tank or something like that, or a fixed size container, or if it is that's pressure size, or if it's a flexible container like a balloon or some sort of car tire or basketball that can stretch slightly, those types of things. All right, so the main gas laws that we're going to be dealing with today is Boyle's law, Charles' law, Gay-Lussec, and we may get to Avogadro's law today. I may put that one in the next video. Just kind of depends on how fast I move with it and as I'm watching time. I'm trying to keep these around 30 minutes. All right. So first thing that we need to know is establish some units that we use to describe gas samples. So volume is typically going to be measured in liters, but it can be in milliliters also. We do want to use metric when we're dealing with this. We don't want to use ounces. We don't want to use things like that. Temperature. This is the important thing. You must always convert to Kelvin. Typically, you're going to be given the temperature in Celsius, degrees Celsius. But to convert from Celsius to Kelvin, it's going to be Celsius plus 273.15 equals Kelvin. So Kelvin is Celsius plus 273.15. Earlier in the year, I gave you a conversion from Fahrenheit to Celsius. If needed, I'll go back and review that as well, just so that you can kind of see what's going on there. And then for units for pressure, the one that I like to use the most is atmosphere. However, the SI unit is kilopascal. And then, so these are the main ones you'll use, but you'll also see PSI, which is pounds per square inch. You will see something called millimeters of mercury. And then an equivalent unit of that, millimeters of mercury, are also sometimes called torr. If you watch the news, when they're referring to weather and pressure, sometimes they'll use bars and millibars and things like that. We're not going to really get into those, but there is a conversion factor between atmospheres and millibars, or atmospheres, millimeters mercury and millibars, things like that. It's just not as common of a unit. So conversion factors that you need to know. All right. Typically, it's easiest to bring everything back to atmospheres. So 1 atmosphere is equivalent to 101.325 kilopascals. Now, remember the difference between a kilopascal and a pascal. 1,000 pascals equals 1 kilopascal. So you see this conversion right here. 1 atmosphere is 101,325 pascals. Those are the same. It's just a difference between a kilopascal versus a pascal. All right. Then another conversion is 1 atmosphere is 700 millimeters mercury. 760 millimeters mercury. 1 atmosphere is 760 torr. So 1 torr equals 1 millimeter mercury. Those are interchangeable. Now, so just to kind of talk about this in another way, if I needed to go from millimeters mercury to kilopascal, I don't necessarily have to convert to atmosphere first. What I could do is say that 760 millimeters mercury equals 101.325 kPa. All right. So we can do that, and we can set up a relationship like that. So, if I was going from kilopascals to millimeters mercury, I would have 760 over 101. If I was going from millimeters mercury to kilopascals, I would have 101 over 760, something like that. So don't feel like you have to always go to atmospheres first. A lot of times I like to do my work in atmospheres because these present a cleaner number or a smaller number, and I just like doing the math with smaller numbers a lot of times. All right, so jumping into this, Boyle's law. So here's the statement for Boyle's law. Boyle's law states that at constant temperature, so temperature when we're dealing with Boyle's law, temperature does not change. All right. So temperature is held constant. Temperature is fixed. So at constant temperature, the volume of a gas increases as the pressure decreases. Or the other way to say that, if the volume of the gas decreases, the pressure increases. So what this tells us is that this is an inverse relationship. All right. As one goes up, the other one goes down. So here is the formula, or here is the setup that you need to know for Boyle's law. P1 times V1 equals P2 times V2. If we were to graph a Boyle's law type problem, what we would see is we would see a graph that produces a curve like this. So as volume is really misspelled there. Um, um, I must have got distracted when I was making that slide. Anyway, so as pressure increases, volume will decrease. Well, volume will get infinitely smaller. So if we're looking at it on this side of the chart, so volume reduces as we increase the pressure. On the other side, as we reduce the pressure, or as we increase the volume, pressure gets lower and lower and lower and approaches zero. All right. So that is Boyle's law. So if you can kind of think about it, if you've ever had one of the water bottles and you take the water bottle and twist it, as you're twisting that water bottle, the volume gets smaller, like you half the size of the bottle, but what happens to the pressure of the air that's inside that bottle at that point? It increases, and that's when you take the lid and you pop it off. Um, so, um, so that's Boyle's law. Now, let's look at an example problem. I will include some practice work for this, but you don't have to do the practice work. I'm not going to grade it. It's just more for you to kind of do some practice. So let's look at this problem right here and kind of break it down. So remember, we're using P1 times V1. So this is the initial, or the beginning conditions, versus initial conditions have to equal the final conditions. All right, so a sample of oxygen gas occupies a volume of 250. I'm going to call that my V1 at a pressure of 740 torr. I'm going to call that my P1. What volume, so that's my V2, will it occupy at 800 torr? P2. All right, so plugging, all you really have to do is pick out what numbers are what's your unknown, what are your givens. So plugging it in, I have 740 times 250 milliliters equals 800 torr times V2. So to get my solution, I'm simply going to take these two, multiply them, and then divide by 800, because I need to get rid of 800. That will get rid of torr, leaving my only units as millimeters. So take a minute, go ahead, try to solve this, and then check your answer with me. All right, so the answer you should have come up with is 231 milliliters, preserving sig figs. All of my info here had 3 sig figs, so that's where we get that. All right, let's look at a couple of other ones just to kind of give the practice and practice identifying. So I'm going to just kind of pull out my givens here. So a sample of carbon dioxide occupies a volume of 3.50 liters. So I have 3.50 liters. I'm going to call that my V1. All right, at 125 kilopascals. So P1, 125 kPa. What pressure, so P2 is our unknown, would the gas exert if the volume was decreased to 2 liters? So my V2 is 2.00 liters. So a couple of things to kind of look for first. First off, make sure your volume units match. If not, you need to get them to the same thing. So if I had one that was in milliliters, the other one is in liters, I would need to either change them both to milliliters or both to liters. And same thing here, since our pressure is in kPa, I'm going to go ahead and just solve for kPa. I'm not going to change units unless I have to. All right, there is going to come a point that it's going to become necessary to change pressure to atmosphere, but that's only when we get to ideal gas law, which would be tomorrow or the next day's material. All right, so plugging this in, P1 is 125 kPa. V1 is 3.50 liters, and I'm setting that equal to P2 times 2.00 liters. All right, so go ahead, pause it, and take a moment and try to solve it, and then see if your answer matches mine. So pause the video, solve the question, and try to answer the question. See if your answer matches mine. All right, so first step I would do is I'm going to remove the 2 liters from this side, getting P2 by itself. So 2 liters divided by 2 liters cancels there. That means that I'm going to divide this side by 2 liters. Now, I want to multiply this first and divide by 2 liters. Sorry, wrong thing. I canceled the wrong thing. I'm canceling liters here, and that leaves my answer as kPa. If you do these correct, it should always check out. All right. Now, just kind of looking at this and looking at this answer, I've got 219 kilopascals. Again, we're maintaining 3 sig figs. The actual answer in the calculator was something like 218.7, 218.8, something like that. So I just rounded to get to there. Now, before I move on, I do want to talk about the conditions that, remember, it says Boyle's law talks about that pressure and volume are inversely proportional. So what we need to look at is what's happening in each condition. So from P1, we have 120, let's look at volume because that's the one we have both things. So we go from a volume of 3.5 to 2. So volume decreased, right? So what does that mean that the pressure should do? The pressure then should increase. Did the pressure go up? We had 125. We now have 219. Looking at this one, just kind of looking at the conditions. Pressure went from 740 to 800, so pressure increased. That means that volume should decrease. So we went from 250 milliliters to 231. That follows the law. All right. Let's look at another. Setup here. And so we have ammonia gas occupying a volume of 450 milliliters at a pressure of 720 millimeters mercury. What volume will it occupy at standard pressure? Now, frequently in gas law problems, we're going to see something called STP, standard temperature and pressure. Standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere, which is equivalent to 760 mmHg. All right. So standard pressure is 1 atmosphere, but that's equivalent to 760 millimeters mercury. So because this one was already in, because our P1 was already in millimeters mercury, I'm going to leave it millimeters mercury. All right, that's just easy enough to save us some trouble. All right, so this is our V1, this is our P1, this is our P2. We're solving for V2. So just setting it up. If you want to, go ahead, pause the video right here. I'm going to go ahead and go through and set it up and solve it, and then you can check your answer. So pause right now, and then we will see how we did. All right, so whenever I do this, I got 426 milliliters. Setting it up again, remember millimeters mercury is going away, leaving us only with milliliters as our answer. No need to change units on any of this. Again, kind of looking at the conditions, pressure from initial to final pressure increased. So that means that predicted volume should decrease because they're inversely proportional. So looking at this, pressure went from 720 to 760. Volume went from 450 to 426. That is a decrease, so that matches. I'll leave these up if you just want to take a snapshot and try them, just for extra practice or anything like that. You can pause the screen, get some of these down, and just try them. Again, always look at what happens to the conditions. So not even answering the question, we have, if we call this P1 and if we call this P2, it's going from 75 to 150. So that means pressure is increasing. So by prediction, that means our volume should go down. So your answer should be less than 175. Looking at this one, we have 1.5 atmospheres to 0.5 atmospheres. So if I call this P1 and I call this P2, that means that pressure is decreasing, so volume should increase. And this is actually our V2. We're actually solving for V1 in this one. All right, because if you read it, a sample of hydrogen at 1.5 atmosphere had its pressure decreased to 0.5 atmosphere, producing a new volume of 750. What was its original volume? So what is V1? All right. Again, just go through there and try to predict what's happening, solve them, things like that. All right. Second gas law is Charles's law. All right. Charles's law says that at constant pressure, so this time pressure isn't changing, we're only manipulating volume and temperature. So as the volume of a gas increases, the temperature of a gas increases. Or as the volume decreases, the temperature decreases. So this one is a direct relationship. So as one factor increases, the other factor has to increase. So when we graph this, this produces a straight line. So just to kind of put this in context, so if you had the fraction 1 over 2, and I want to maintain the same value, I want to set up an equivalency. So if I increase this to 2, what does my new denominator have to be? Well, I doubled the top one. That means I'm going to double the bottom one, so that's 2/4. The other direction, and this is going to look weird because you're not used to seeing a decimal in a fraction. But if I half this, then I would have 0.5 and 1. All of those are the same thing because 0.5 divided by 1 is 0.5, 1 divided by 2 is 0.5, and 2 divided by 4 is 0.5. So they're all the same thing. Now, putting this in real-world context, What we see this one is volume and temperature. Think of a hot air balloon. Um, Whenever they have those burners in a hot air balloon, you have the air inside the balloon. You heat up the air, it expands. It causes the air to become less dense and then less dense in the surrounding air, and then allows the hot air balloon to float. Um, as the air on the hot air balloon cools, the air molecules become more dense, and the volume of the air reduces. Therefore, the hot air balloon starts falling again. All right. So looking at a couple, so let me go back real quick. So the formula that we're using for this one is original volume over original temperature equals new volume over new temperature. One of the things that we have to remember is temperature must be in Kelvin. All right. Change temperature to Kelvin. If you don't, you're going to have some problems. All right. So again, Charles's law states that the volume of a gas is directly varies with the Kelvin temperature, assuming that pressure is constant. So we have the setup that we can have V1 over T1 equals V2 over T2, or we can manipulate it and say V1 times T2 equals V2 times T1. Remember that the conversion from Celsius to Kelvin is Celsius plus 273. All right, so let's look at this example real quick. I'm going to do 3 examples off of here and then we'll move on. A sample of nitrogen gas occupies a volume of 250 milliliters, so that's my V1, at 25 degrees Celsius, that's my T1. What volume, V2, will it occupy at 95 degrees Celsius, T2? All right, so looking at my givens, I have some issues here. What's the first thing that I need to do? That's right. Temperature is in Celsius. We need to change that to Kelvin. So all I'm going to do is add 273 to each of these. So we have Kelvin temperature on this one is 298. And for this one is 368. Okay. All right. Now I'm just going to set up my equation. And so I have 250 milliliters over 298 K equals V2 over 368 K. All right. So go ahead, take a moment, solve, see if your answer matches mine. All right. So solving this one, first thing that I'm going to do is I'm going to multiply each side by 368 to get rid of it from this side. So 250 times 368. That's also going to allow me to get rid of my Kelvin units. And then I will divide it by 298. And that's going to give you an answer of 309. Remember, we're trying to maintain 3 sig figs. I know your temperatures are only in 2 sig figs on this one. I'm going to go with the statement here, since your volume is in 3. Actually, we probably should go 2 on this one, just noticing that this is 250. There's no decimal right there. So 310 would be your actual thing because the original was 308. All right, so you can do that. But really and truthfully, your temperatures, when it's in Celsius and we go to Kelvin, you can actually use that as a 3 sig fig if you choose. Excuse me. But just go ahead and pay attention to what's there. All right. So looking at this one, oxygen gas has a temperature of 40 degrees Celsius. So T1 is 40 degrees Celsius, which is 313 Kelvin. All right. When it occupies a volume of 2.3 liters, so V1 is 2.3 liters, to what temperature should it be raised to occupy a new volume, V2, of 6.5 liters? All right. Now, so that means we are solving for T2. All right. Go ahead, set up your problem and solve, and then go from there. So pause the video, set up your problem, and solve and see what you come up with. All right, so don't be scared by the answer that you got on this one. If you came out with a number that just seems ridiculously high, that's to be expected because we are making a very significant change to the temperature right here. So, I mean, to the volume right here. We're tripling the volume almost. So that means that we're going to triple the temperature as well. So just kind of think about it in that context. One way to look at it is we're increasing the volume by a factor of 2.8. So that means that we have to increase the temperature by a factor of 2.8. So 2.8 times 313 gives us the new temperature of 876, which is 880. And then if you convert that back to Celsius, it's 610 minus, subtract 273 from that. All right. Again, we can look at this in the relationship. So volume, excuse me, volume increased, so that means that temperature had to increase. In this one, temperature increased, so volume had to increase. All right, I'm going to pull this up so that you can kind of look at some of these other problems. Just if you choose to do the practice on it, you can. I'm not going to go through and answer. If you have specific questions, email me and I will give you those. All right, so that's Boyle and that's Charles. The next one is Gay-Lussec. Gay-Lussec he just took the other side of it and he compared pressure and temperature. And he found out that pressure and temperature are also directly proportional as long as you keep the volume constant. So this is in a fixed container. The container cannot change size. So this would be like a propane tank or something like that. If you were to take, and some of you may have experienced this or anything like that, where if you have some cans of soft drinks in your car, you leave them in the car. They're not in an ice chest or anything like that. So they're just in a hot car during the summer, and you might have come back and that can has exploded in your car. That's because as the temperature increased, the pressure inside the can, the gas pressure inside the can also increased and caused it to reach a point where the can fails. So again, looking at the graph of this is going to produce a straight line for the graph. All right. Remember that temperature must be in Kelvin. That's a necessary change there. All right, so for Gay-Lussec, we have P1 over T1 equals P2 over T2. Remember the conversion from Celsius to Kelvin is Celsius plus 273. All right, so let's look at some of these problems and go from there. So solve the following problems assuming constant volume. So we have a sample of gas in a closed container that's 100 degrees and 3 atmosphere, so 373 Kelvin. 3 atmosphere is heated to 300 degrees, 573 Kelvin. Notice that the temperatures are 4 sig figs there. The pressure is only 2 sig figs, so our answer is going to be in 2 sig figs. What is the pressure of the gas at the higher temperature? All right, so this is T1, this is P1, this is T2. All right, so plugging this in, we have 3.0 atm over 100. No, almost did it wrong. We would have come up with the incorrect answer there. 373 Kelvin equals 573 Kelvin and P2. All right. So again, take a moment, pause the video, solve it, see if your answer matches mine. All right. So if you did this correctly, you should have gotten 4.6 atmospheres, and going from there. Again, I'm gonna let you look at some of the problems. If you choose to do them on your own and practice, you can do these on your own for practice. So pause the video, look at it, and then unpause it when you're ready to move on. All right, so we just went through Boyle's law, Charles's law, and Gay-Lussec's law. So some of the ways to just kind of help you remember it. Remember that Boyle's law, temperature is held constant. So think about a BLT. Boyle's law, temperature is constant. The constant for Charles's law is pressure. So Charles's law, think CP, cheese pizza. And for Gay-Lussec's law, volume is constant. So think about your green veggies. That volume is constant in Gay-Lussec. That may or may not help you. Sometimes it just helps me to remember what variables are involved in each of these equations. Now, really and truthfully, you don't have to memorize these three laws separately. The only thing that ever happens is sometimes they'll ask you a question about what is Charles' law, what is Boyle's law. But we have done something where we have these three equations that we have PV equals P2 V2. We have V1 over T1 equals V2 over T2. And then we have P1 over T1 equals P2 over T2. And what someone observed, what they observed in physics, is that we can combine all three of these and get the combined gas law of P1 times V1 over T1 equals P2 times V2 over T2. And we can look at all three variables at once. What this one allows us to see is, remember that pressure and volume are inverse, but pressure to temperature or volume to temperature is direct. And we can see that if we change two variables, say we change pressure and temperature, which one's going to have the biggest impact? In this case, volume, thinking if we increase pressure, volume should decrease, but if we increase temperature, volume should increase. Well, which one has the biggest impact? Well, we have to solve for volume and see. If volume increases, that means that temperature had the biggest impact. If volume decreases, then pressure had the biggest impact. So again, combined gas law is the other gas laws just put together. So if we're looking at it this way, we're just looking at Gay-Lussec. If volume is held constant. If temperature is held constant, then we're looking at Boyle. If pressure is held constant, then we're looking at Charles. So that's all that really is. So we can do that at the same time. Now, if you think about it, if your volume remained constant, you could still use combined gas law and notice that the volume is going to cancel itself out. Or if temperature is constant, temperature would cancel itself out. So you can always use the combined gas law in any instance that you would either need to use Charles, Boyle, or Gay-Lussec. All right, so we'll do one problem with combined gas law, and I believe that's where we're going to stop today. We'll pick up with Avogadro tomorrow. All right, so it says a sample of nitrogen monoxide has a volume of 3.0 liters, so that's my V1, and a temperature of 20 degrees Celsius, so that's going to be 293 Kelvin. Don't judge me if I did my math wrong, my addition wrong right there. I'm just trying to be quick with this. And a pressure of 1.5 atmospheres. All right. What volume? What volume will the sample occupy at 30 degrees Celsius? All right. So this is P1. This is T2. And P2, we are solving for V2. So all right, and so this one is 303 Kelvin. All right, so setting this up real quick, we have 1.5 ATM times 3.0 liters over 293 Kelvin. And we're setting that equal to, I'll draw a line right there so I don't cross over. Setting that equal to 2.5 ATM times V2 over 303 Kelvin. All right, so go ahead, pause the video, solve for your answer. I'm going to change colors just to make the answer a little more visible, and then just check your answer with that, and then I'll show you some problems for you to practice. All right, so looking at this one, P2 equals 1.9 ATM. I forgot to cross my T originally, so I extended it. That's not, don't worry about that. Just bad handwriting. So looking at this, let's look at what actually happened here. So pressure increased overall. Temperature increased. So by pressure increasing, we would expect volume to decrease. Ooh, I did that wrong. It's not ATM. That is actually liters, 1.9 liters. All right, so by pressure increasing, we would expect volume to decrease. By temperature increasing, we would expect volume to increase. So let's look at what actually happened. Volume went from 3.0 to 1.9. So volume decreased. So that meant that pressure had the most influence. All right, so pressure was the biggest factor there. And if you really look at it, we only had a 10-degree change in temperature, But we had a 10-degree change in temperature, but going from 1.5 atmospheres to 2.5 atmospheres, we the doubled the atmospheric change. That's why atmospheres had the most impact. If you were looking at this in terms of looking at it in millimeters mercury or something like that, you would see how huge the difference in these two numbers in atmosphere are. All right, so go ahead, look at some of these other problems, pause the video. You can try these. If you have questions, ask me an email, um, make comments in the Google Classroom, whatever. I can come back and I can either send you the answer key or work some of these if need be. All right, so going to the homework problems for Chem 101. You should be able to answer questions 5, 6, 7, and 8 right now. Some of these I didn't directly teach. Like there's some where you're converting from millimeters mercury to kilopascals or millimeters mercury to atmospheres, things like that. Just, you should be able to go back to that original slide and see the conversion factors and do that. There might be a question in there about a manometer. I am going to go back and go through that, and I'm also going to add another little video, short video, that deals with those first couple of questions 1 through 4 that are talking about kinetic molecular theory and things like that. I tend to do kinetic molecular theory with ideal gas law, so you're going to see that in day 2 that I'll cover those concepts. All right, so good luck.